Okay, good afternoon, everybody. I'd like to introduce myself. My name is Neil Stevenson. I work for a company called Hazelcast, and my talk today will be about a product called Jet from Hazelcast and how you can use this to do in-memory streaming. Because in-memory is fast, and streaming is what we want to do. So a very brief outline of Hazelcast, the company, what I do, why do we want to stream, really just to set a bit of context. Then I'll run through the classic example of streaming is always word count, because it gives you some very interesting concepts. And then a bit more of a realistic example, which is up on GitHub, and you can download if you want to do that. You can try it yourself. I'll try it today, and hopefully it'll work. You can never tell with live demonstrations. So Hazelcast, the company, it's been around since 2008. We're now based out of Palo Alto in California. I'm based out of London. The software itself, you can download from GitHub. You can run it. It's Apache 2 licensed, so feel free to do so. And my role in the company is I'm solution architect. I help organizations get started with Hazelcast. I help organizations tune and optimize the Hazelcast setup. I do conference talks. I write Hello World very many times. I run Hello World quite a few times. And I drink a lot of coffee, an awful lot of coffee. So that's me and us. But now, Jet. Jet as in jet engine. It doesn't stand for anything. It's not JET, it's jet as in fast. The core concept that we're looking at is a directed acyclic graph. On my diagram, it's going from left to right. Data flows through the system. Now, some of you will probably notice that I'm not the youngest person in the room. When I started working, we had an overnight batch. You would put all your things into a database, and then you would process them overnight. And that's kind of unacceptable these days, because overnight is just too slow, but any kind of batch is too slow. And there's a secret problem that you're storing data to process. Why do you want to store it? Storage costs money as well as time. So perhaps what you want to do is process the data as you receive it and store the results, rather than store the input, store the output. And that's where Jet comes into play. Jet has an architectural pattern based around a directed acyclic graph, where you're writing little pieces of code, little functions that take a little bit of input and produce a little bit of output. And you chain these together to make your processing. Now, because it's Hazelcast, it runs in memory, and that makes it very, very fast. As anybody who was in the previous presentation will know how slow disks are compared to how fast memory is. So where Jet fits in the big picture, there we go, is you might have Jet as a processing pipeline in the middle of your architecture. You've got a data feed coming in of transactions, of measurements, of whatever. You will process that, perhaps enriching it as it comes along, adding extra input in from elsewhere, stored results, and send it out. Produce an alert, produce a report, persist. So if we look at that more closely, what we're talking about is a flow of data from place to place. Each of these processing nodes, the black circles, what we call a vertex, takes a stream of data in and produces a stream of data out. The vertices at the end are producing your final result. The vertices at the start are producing your input. So everything essentially is a function that takes input, and a function that gives output. It might take more input than output, less input than output. Overall, you're kind of expecting to reduce as you go along. You've got a flood of data coming in, and you're reducing it down to a trickle. And the other part of the directed acyclic graph is the edge, the lines that connect the processing. So this is just a pipeline. We're saying output coming from this box here goes to both the next stages. So we can split, we can duplicate, we can send serialize, various configuration options. So this is what JET is about. It's about stream processing. It's about caching, maybe. When you think of what a cache is, most people think of a cache as just a faster copy of data that's elsewhere. The data doesn't have to be elsewhere. If this is the result of a calculation, then you've got a materialized view, maybe. So this is where you have to think of things differently. The data that's coming in and the data that's going out, you might just be reformatting it. So, in a nutshell, JET is stream processing. It's in memory and it's distributed. So as many machines as you've got, you might run it. On my example, I'll run 2 instances and they'll play nicely together. It's a team of 2. You might decide to have a team of 4, a team of 6, whatever is appropriate based on cost and performance. If 2 nodes can do a certain amount of work, then 4 nodes can do twice as much. 8 nodes can do more, 12, 16, whatever. So no talk on stream processing is complete without word count. For this example, I've gone with Hamlet's speech by William Shakespeare for no particular reason, but most of us will remember, if we've ever heard it, it's to be or not to be, blah, 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 and I can't remember the rest. So the word be occurs twice in the first sentence. The word the is, it's on line 1, it's on line 2, etc. So unsurprisingly, the word the is the most common word. So why this is a good example. So if we were to do this just raw Java, this would be how we would process it. So we're taking a stream of words, we're flattening the lines into individual words, we're ignoring the case, we're filtering out actually the short words, so that and be, we are not really actually that interested in, and we're just counting them up. This is a Java 8 stream. But it's just a pipeline, really, if you think of it. What we're taking is a line of text and then sending it into something that translates it from one line of text into a collection of words. So splitting it up. And then for each of these words, we're just counting them, accumulating them. Map reduce. Now, the problem with that is that these stages will all block because they don't have anything between them. And this is where we start to get into the design pattern. If we remember the previous talk, queues are empty or queues are full, rarely anything in between. So we can buffer the data coming from one processing node to the next using a queue. And then if we look at this a bit more cleverly, you know, this is just still just single-threaded, really. Why don't we break it into 2? Why don't we split apart this part of the work that separates out the lines into the words? Well, you can do line 1 in one CPU and line 2 in another CPU, because line 1 and line 2 got nothing to do with each other. This is where it starts to become faster. And then counting the words, we can also split up. We could have one CPU counting all the words that begin with F, another CPU counting all the words that begin with G. And then we can take advantage of multiple CPUs because parallelization makes it faster. And where we make it faster still is across multiple machines. You've got multiple machines in your data center, so we can split the lines of text across multiple machines. That's easy to do. Each machine takes a line of text and then splits it into some words. It locally collects the words and then globally collects the words. So there's a little bit of an optimization. You can say, let's count how many times I've seen the word the, and then you count how many times you've seen the word the, and we add them together at the end. So we can map things to a central point. But word count isn't particularly interesting. The one we want to look at today is exchange rate calculation. If people are trading on foreign exchanges, you want to know what's happening with prices. Now, this is why we want stream processing, because the prices are changing all the time, going up and down, up and down. And so it's a stream of prices will come in. And what we want to know is what's happening to the prices. Individually, the changes are too small. You know, there's too much happening. You miss the big picture. The big picture is you want to know, is the price going up? Is the price going down? Or really what you want to know is the price gone over a hill or at the bottom of a hill heading up? Is there a change in direction? If you're a trader, the price is going down, you want to sell it. Price is going up, you want to buy it. I had to think that one, right? You've got to get it right way round. And this is where averages come in. So what we want to do is calculate moving averages. You know, what's the last 10 results? Add them up, what's the average? That gives us a better indicator than each individual price. And there's various ways of calculating the averages. Just straightforward, simple average, add 10 up, divide by 10. Or you can do like an exponential basis where you put more weighting onto the more recent ones. We'll do it both ways. So we're processing a stream of data. So the input is a stream of prices. What we're calculating is the average. And this is where we're now starting to say, are we caching the average? Is that a materialized view? This is a stream of data coming in, and we're holding something that's derived. Holding, we're not even bothering to store it forever because we don't care. But this is just a trading indicator. And this is my data set. I got this from the European Central Bank. Every day they produce prices. So it's the price of the euro against the US dollar, the price of the euro against the Japanese yen, and various other currencies. There's about 30 or so they produce. So this gives us the exchange rates. So what it's actually giving us is 90 days of closing prices. It could be 90 minutes, 90 seconds. Doesn't matter. There we go. So what we actually get in our stream of data is a currency pair. It's the euro against the dollar, euro against the British pound, and the actual rate. And what we want to do is batch them up. As I mentioned, we've got a stream coming in. We're just interested in a time window. We want 10 of them. So it's the euro against the pound, 10 different measurements. It could be 10 measurements of temperature, 10 measurements of anything. And we can partition this up because we want to calculate the simple average, add them up, divide by 10, and a weighted average, where the last ones are given higher value. Well, we can do that independently, and we can do that on multiple CPUs. So this is what I'm meaning by the streaming. Every section of the processing is just doing a little bit of work. And in this case, we're actually going to store the results in Hazelcast, which is no great surprise. But the power here comes on the scaling. We can duplicate that directed acyclic graph, that little chain of processing, we can run on multiple CPUs, multiple servers, because we can partition the work. We can do the average for the US dollar, and the average for the Canadian dollar, and the average for the Swiss franc, and the average for the Japanese yen. So that's 4. If we've got 2 machines, you can do the dollar on one and the yen on another. If you've got 4 machines, you can partition it out, because the work is independent of each other. That's where you're going to get the benefit. So let's actually see the code. The code is on GitHub. I'll put this on the last slide as well. And you can download it, have a wee play. This is what we want. Our prices, I saw this in the street today. Oops, sorry. So let's go to the code. Can we see mine? Right. My display is not visible. Displays. Result. Okay. How do I get rid of that? That's it. Okay. I'm an Eclipse user. So how do we actually do this? Up better, a bit clearer. Anybody that's ever run Spring Boot, this is how we create a Spring Boot application. Dead easy. And this is how we configure Hazelcast. An XML file. We're really always saying is, where are the processes? I mentioned it's multiple processes. Well, whereabouts are they? They're all going to run on my laptop. And this is how they find each other. They do a ping out and saying, is there anybody there? If you find somebody, you join together, collaborate. So it's one XML file so they can find each other. And the last piece of magic, we load that XML file. Three lines, create a Jet instance. It's as easy as that. So if I run that, Spring Boot creates you an executable jar. I'll start that up. And I'll do another one in another window. I'll do 2. So I'm going to run 2 processes on the same host that will find each other once you start up. Spring Boot 153, the latest and greatest if you don't use version 2, which is still in beta. So here is the server started up. This is who it thinks is in the team. In a second, the other one will start, they'll join together, and they'll both log out that they've joined together. Let's wait for that to happen. Here we go. Here's the ping coming in. So they've established connectivity, and now the group, we're running 2 instances of in-memory storage that are going to collaborate in terms of work sharing. I'll now start up my client, because it's kind of like a client-server model. You don't have necessarily a database. You could have a database as well, but it's like in-memory storage sitting in Java processes, which I connect to from my client process. My client process is also Java, because that's really the only language I know. And let's wait for it to start. So the client does the same kind of thing. It's all wrapped up in Spring. It's found the servers. It's connected to them. It's up and running. Now, this is the XML that you get in from the European Central Bank. But let's go and run my client. I mentioned Java is all I know. I don't know web design. Well, so that's okay. You know, it does the job. It's not about the GUI, is it? You can do a better GUI than that. I'll challenge anybody to do a worse. So we've got no currencies. So what I do is I go and click the load button. That will connect to the European Central Bank right now and has found 1,922 items of currencies. These are stored in memory. They're cached. And if we pick Australian dollar, it gives us the closing prices. So what that's done is that's materialized the view. That's taken an XML file, this XML, and turned it into Java. Stored that as Java objects in memory. So we've done a bit of transformation. And now what we want to do, I'll run the calculation, then I'll show you the code. We'll run the moving average analysis. And we calculated the last 10 times, and it took us 8 seconds. It's running on my laptop. It's not massively fast. And if we look at the simple moving average, so you take the last 10 results and add them up and divide by 10, then the euro against Australian dollar comes in at 1.5. Nice. And exponential also comes in at 1.5. That's not a great example. Then let's go try so the next one down, well, let's try the Canadian dollar. 151. That was exponential, 151. Am I displaying different data? That one's bound to be different. Indian rupee, 148.50. Yay, slightly different value. So there's different calculations give you different value. But, so it works. There's our answer, but how does it actually do it? And this is where the directed acyclic graph comes in. So, moving average directed acyclic graph. Let's see, actually, it'll display a little bit better on GitHub. Scroll down, this is just what I'm doing. Here we go. So we have stored the reformatted prices. We're passing them in. Now, when you're reading them from an IMAP, which is just a map, they're coming in randomly because maps aren't ordered. So then you've got to sort them and collate them. And then you've got 10 prices. You can then send 10 prices to the simple moving average calculator and 10 prices to the exponential moving average calculator. And it will store them in other maps. So it's materialized them again. So what we're holding is the result of calculations, and that's where you might not think that to be caching. And because I'm running this on multiple processes, if I look at the server logs, then I can see that I have done the Japanese yen and whatever the SGD is on this one. I have done, let's pick some that actually recognize New Zealand dollar on this machine, and on this machine for the back. I've done the British pound and the US dollar and the what's that? Don't know some of these, Swiss franc. So different servers are doing different currencies. And I create my DAG as Java. There's a lot of Java docs in there, but basically I'm creating a processor that reads from a map, takes some data in from a map, and a processor that calculates the last 10. In this case, it's the last 10, but I'm just passing 10 as a parameter, and an edge that connects the two. And this edge is partitioned, meaning use the currency to dictate where it goes. So if we go back to the slide deck. So Jet is easy to add. Just a Maven dependency. 0.31 is the current version. 0.4 comes out in June and adds time windows, so it does this for you. But when you're creating these nodes, where does the data come from? Well, in this example, it was Hazelcast because I wasn't sure it was going to be internet connected, but you might read it in from Kafka. Most likely, Kafka seems to be the transport of choice. Or you might read it in from a WebSocket. Or you might construct it from somewhere else. Basically, it's a processing chain. If you're the source, you don't have anything coming in. You're just producing data. And if you're the sink at the other end, then all you're doing is consuming data. So you can write your own. And this is a bit my code, and it's like, it's okay. Read, is it easy? Maybe not. So we have like a two-layer approach. Think of this kind of like the assembly language. This is the underneath. If you need the power and the actual precision and you want to do it the hard way, this is the way. So if we want to be easier, we want to do streams using Java util stream. So this would be, we saw this earlier. I've just colored it in blue. This is how you process on Java util streams. And this is what you change to run it in Jet. So as a developer, really all you're changing, I'll toggle backwards and forwards, is just you're streaming data in from a map. And it's an IMAP, it's Hazelcast's map. And you're streaming it out to a map. And that's all you've changed. Because the problem with Java util stream is it isn't serializable, it isn't distributed. So it'll use all the CPUs available to that JVM, but it won't know about anybody else. So this is what Hazelcast has done with the Jet. This is the part that makes it easy. Just plug it in, and now it connects up multiple machines. You saw how easy that was. So what we've done is we've provided an implementation distributed stream that provides all the functions of the Java stream, but runs them across multiple machines. So that allows us to create code like this. Very easy, just standard code really. Easy to write, easy to maintain, but it runs efficiently using all the CPUs on all the machines you've got. So there's like a two-tier interface in Jet. You can write the actual individual bits yourself, and Jet does all the rest of the stuff. Or you can do it at more high level. Stick to your Java style that you're familiar with. So that's the difference. You know, this is, if we look at something like the filter, filter is just a function that's a true-false. And the Java stream one takes a predicate and returns you a stream. The Hazelcast one at the bottom is a distributed stream. It's an extension to the API, and under the covers, it all runs out for you for no effort at all. Very easy. So, a very brief slide. You can go look at this on the website. But fundamentally, what we've got is a client that connects to a grid, and the grid does the processing. The client here is Java, but the client can be other languages. That's what we're working on. So it's an open protocol between the client servers. You can serialize your data. You could probably run it from Node.js. Seems to be very popular. And you've got a version of the Java util streams. And then you've got underneath, you've got the power if you want to dip into the API. So it's very fast, easy to get going. You can download my example, connect it up to Hazelcast itself, obviously, but we're planning other connectors because this is still a work in progress for us. It's free software. Download it. Now, it's very, very fast. For word count, at least, we're beating Spark and Flink. We're even beating our previous version. We're kind of tweaking it. So it's super, super fast. But it's all Java-based, so you don't have all that nonsense with Zookeeper and all that difficulty of getting it set up. It's just dead easy. Just one XML file. The processes find each other, connect. Simple. So this was how you could run this word count. So what we're seeing is we're sending data within the same JVM. That's the fastest. And where necessary, you send it to other JVMs. So for a word count, this is us calculating subtotals and passing them to a central point to calculate a grand total. So we did a very, very quick coverage of what Jet is. We'll have another look at the code in a second, but just a couple of things you've got to think of is, first of all, it's really lambdas. You're running a function that takes a stream of input and gives you a stream of output. You have to provide enough nodes to get the capacity you need. You run it on 10, you run it on 5, you run it on 2. Dead easy. Really, really easy. It's easier, in my opinion, than Spark and Flink. It's faster. It's Java-based. So if you're a Java developer, you're up and running in 15 minutes. You don't have any of that. You could probably download my example and get it running in 15 minutes. So just before we, let's go to that. So if we go back to my code, let's have a look now at what my processing's actually doing. So this is how I'm going to process the prices. I'm getting in a price, and I'm keeping them in this process in an ordinary map. So I'm collecting the prices up. So this is my input processing and a process method. And I'm collecting them into a tree set, so it orders them. And when I'm done, I'm traversing that tree set to spit out the last 10. So that's what my code does for me. This is me producing, taking in a big stream of data, caching it in locally, and traversing it out when I'm done. So this is what you've got to think about is, do you have enough capacity? Because if you're putting that into a map, then you've got as much space as that JVM will accommodate. So there's still a little bit of thinking goes on. You know, it's like if you've got more data coming in than one process can cope with, you go to 2 or 4. But you have to kind of work out what the justification is. But you can only do this if you can split your data across the processes. Doesn't, you know, if the only currency you had was the euro, then you could have 2 processes, but only one is doing the euro, so it's no good. You know, you have to work out a way to partition your data so that you can even out the work. I'm sending one currency down one thread and another currency down another thread. Those threads might be on different JVMs, they might be on different machines. That's the attraction of the algorithm. And the actual processing, all I'm doing is adding them up, closing prices. And when I'm done, all I do is spit them out again. Easy. So I've got one slide left, which is mostly to say thank you, because we're heading towards questions. But before I do, a couple of links for you. GitHub, for this example. My email address, I'm neil@hazelcast.com. You can, you always think of a question afterwards. We'll go to questions in a second. But if you think of a question tomorrow, send me an email. You can download Jet from GitHub. You can look and see how we're doing it. And you can raise questions in Stack Overflow. You know, how does it work? I'm trying to get this going. How does it work? That's what we're here for. Okay? So, questions?
Hi. In your high-level example, when you use Java approach with streams, do you have distribution between steps of your algorithm?
Yes. So, if we go to, go back, this example, did you mean the word count example? So, what I've done is I've got a feed coming in of prices. Now, in my example, it's a single feed, and I'm splitting them out using the currency. So all the A's go here, all the B's go here, so the Australian dollar goes to there, and the Belgian franc goes to there. If you've got, doing an algorithm like that, you're splitting it into 26, say. Well, if you've got 26 servers, that works nice. If you've got 27 servers, you've got one idle. So you have to be careful that you split sensibly.
Sorry, I meant your example when Java streams, not this slide.
So,
Java streams.
okay.
Yeah.
That
yeah,
one.
That's exactly.
Yeah. So what happens with a streaming map is a Hazelcast map is distributed. It's spread across multiple processes. So it's streaming that data through a JVM because that's, it never sits completely in the JVM, it just passes through. Not quite answer your question, or?
So you have one stage here, or is it or like first it's splitted words, then got to next stage, like
yes.
counting.
So you have to be. This ultimately is a directed acyclic graph. You're running that on the servers, so it gets pushed, distributed, executed, and in this case stored. So if you've got the input is partitioned, the output is partitioned, you've got multiple machines, you can process in parallel. That's where the speed comes from. I meant to mention, when we were talking about queues again, between each of these processes, these arrows are basically queues, and Hazelcast implements back pressure. So if the producer is too fast, the consumer will say, you know, the queue is full, the producer gets paused, the consumer gets a chance to take over. So Hazelcast does that for you. It happens fastest when it's on the same JVM, but if you still have back pressure across JVMs, so you don't have to worry. The only thing you really got to worry up, back pressure handles surges as long as you've got enough capacity to get through your result eventually. You know, you can't flood it. More questions?
Hi. Thank you for your interesting lecture. I have a question about multiple nodes setup. If we have multiple nodes, but they not the same configuration. I mean, we have one very fast node and one the less fast. Does JET cares about workload between nodes? So when we partition, the fast node takes a lot of data, and I think you understand what I mean.
Yeah, I get what you're saying. On this diagram here, we've got two machines, say. This is one node, this is another. Hazelcast will use the number of CPUs to determine how many instances of each of the vertexes, each of the processes to run. But the kind of concept around the grid is that everybody's kind of equal, because you have to also think that what happens if one of these machines has a power failure or something. So you don't kind of, you don't want anybody to be more special than anybody else. So generally the best setup is for all the machines to be the same configuration, the same speed, the same amount of CPUs, the same amount of RAM. It's a team where nobody's better than anybody else. So definitely aim towards unification of your servers, make them all the same. If these are virtual machines, then make sure they're all set up the same.
Thank you.
Do you have monitoring tools to see the health check of these virtual servers?
We have some. This has still been built. This is on my roadmap. So we have a management center in Hazelcast that tracks the amount of data that's stored. It's a web GUI. If you go to the Hazelcast download page, you can download and run the management center. But we're still building out JET. So we can. This is why it's on the roadmap. So it's like, what sort of statistics will you get? How? This is why we want you to send us things on Gitter. You know, it's like, we'd like to be able to monitor, is there a bottleneck on a particular job? Is there, are we not running enough nodes? Are we running too many nodes? We're wasting resources. So that is not quite there yet, but it is coming. No more questions? Okay. So last slide. Thank you.